Welcome to our rescheduled, extraordinarily nerdy presentation here. Thank you for taking the time away from the party to come and listen to this talk. I have my eye on all of you guys because this marks you all out as uber nerds. Because like Microcode, super dense. And also super nerd, which is why I totally volunteered to watch this as well. Because this is another thing that I actually, like, from a previous career, which we're not going to talk about, I was very into. So, our lovely speakers are SPQ. Wave for the crowd. Wave for the, wave. And Nspace. And this is EntrySign. Create your own x86 microcode for fun and profit on AMD. They say it's patched. I don't believe them. Because we all know how microcode updates work, don't we? Cool. Very well. Thanks. Big round of applause for SPQ and Nspace. Take it away, guys, and we'll be back a bit later.
Thank you. Yeah, we will talk about EntrySign today and how to create your own microcode for AMD machines. This is Nspace und ich bin SPQ. Yeah, we created a blog post about this topic where you can read a lot more about this, this vulnerability. It's linked here if you are interested. And also, yesterday we got awarded with 2 ponies for best desktop bug and best crypto bug. So yeah, 200%, 200% more ponies. Thank you. We too are not the only ones who are involved in this research. There's a couple more. Some are listed here, but even more than those. Not everyone could be here, but yeah. I will tell you now what microcode is and how all of this stuff works. So a very simple CPU has to do some steps. It first has to fetch some data from memory to execute. Then it has to decode this data into, for example, for x86, into instructions like push and so on. And then it has to execute these instructions. But x86 is quite complicated. This is an excerpt from the instruction manual, and it's a lot of instructions. And instructions sometimes are also very complicated. This is the pseudocode of the return instruction. It's really complex, and it's an instruction that appears very often. Now, so to make this better work, vendors of x86 CPUs decided to introduce something called microcode. On the left side, you see some x86 instructions, and on the right side, you see how those could be translated to microcode instructions. Some instructions are just one instruction in microcode and in x86. Some, like this xlet, are translated into multiple microcode instructions. How this works on the CPU, this is a die shot from the Zen 1 CPU. And what's highlighted in the middle is the so-called microsequencer ROM. This is where some of the microcode instructions are stored. And this engine is kind of complex. Here's a rough diagram of how this works. We start in the top left with an instruction that was decoded. And for example, here we have RDRAND, an instruction. And the first step is to decide if this is a microcoded instruction. If this is not a microcoded instruction, then the so-called fast path is taken in the bottom, and the instruction in a slightly reformulated way is sent to the backend directly. So one x86 instruction just translates to one microcode instruction. If this is a more complex instruction, then it is microcoded. And that means that we take the path into the box in the middle. First, we have to calculate for this x86 instruction, where do we start executing code from the microcode ROM. This is the entry point calculation. When we have that, we fetch an address from the microcode ROM and get something called an instruction bundle. This is the case for AMD. It's always 4 instructions with the modern AMD CPUs and 1 sequence words. The instructions are sent to the backend again and are executed. The sequence word tells the microcode engine how to proceed afterwards. So, for example, it can say just execute the next, just fetch the next instruction bundle from the ROM and continue. Or it could say, we are done with this x86 instruction, just return back to the next x86 instruction. Right, but at some point, Intel had an issue. It was in the 90s or so. They had this fdiff bug. So that was bad. And it meant that they wanted to introduce something to be able to patch this microcode. And what they did is they added some components. I think Intel and AMD are very similar in this area. I don't know exactly, but this is how it looks with AMD. The first edition is in the middle, in yellow. It's the microcode RAM. It is living in the same address space as the microcode ROM, and it just also contains instruction bundles and sequence words. The second edition is at the top left a bit. It's the match registers. They can be understood as a list of breakpoints that contain addresses inside of the microcode ROM. And whenever one of these addresses is being fetched, or should be fetched, instead it will fetch the instruction bundle and sequence word from the microcode RAM at an address that corresponds to the breakpoint number, to the match register index. And the last edition is the so-called mask registers, and they are there to modify the behavior of fast path instructions. When they describe circumstances under which the fast path decision should be changed to say, no, this is a microcoded instruction instead. Yeah, this is how patchable microcode engines look in the case of AMD. Now, Nspace will tell you more about EntrySign.
All right, enough talking about microcode. Let's start talking a bit about EntrySign. So this is how EntrySign was described in the press, how to make the AMD CPU. Always return 4 from a random number, and all of that. So what is microcode? Why is this a vulnerability? Well, if you know anything about loading microcode updates, one thing you would know is that you need root to load an update. So you might ask yourself, why do we even care about this? Why is this important? Like, if you need root, what's the problem? Well, the thing is that there are some scenarios in which, even though your attacker has root, this is still like kind of a valid threat model. And one of them is confidential compute. Confidential compute is a set of technologies that AMD, Intel, ARM, other CPU manufacturers came up with that lets you run your data or your code, your VM, in public clouds such as GCP or AWS. And even though you don't trust the owner of the cloud, the CPU will still defend the data that is in your VM and will prevent the cloud provider from tampering with the data in your VM or reading it. And in this, in AMD's implementation of this, which is called SAV-SMP, the microcode is considered trusted. So if you can load your microcode in there, this is completely broken and you can do anything you want to the VM. Another thing is something called SKInit or DRTM. SKInit is the name of AMD's implementation, which is something a bit like secure boot, where the OS can ask the CPU to reset itself to some known good state when it boots. The idea is that if you got infected by some bootkit, the OS can ask the CPU to just wipe everything and go to a clean slate state, which is secure again. And again, if your bootkit is loading some malicious microcode, then you can patch this SKInit instruction to not do anything, and so the bootkit is still there and the OS is still compromised. So this is another case in which you care. And most interestingly, most importantly for us, and perhaps for you, is that you can do research on the CPU now. You can poke at all sorts of internals that were hidden before. You can do funky stuff like make RDRAM return 4. You can, somebody a few years ago did something like this on Intel, because there also was was a bug that lets you load microcode on some Intel CPUs. They implemented pointer authentication on Intel. They did all sorts of fun things. And now you can do this on AMD too, which we think is pretty fun. OK, but how do we get there? Well, the first thing is that we started by just looking at microcode patches from AMD that are publicly available now. So first of all, we want to get some microcode patches from somewhere. And thankfully, somebody did all of the hard work and collected all existing AMD patches on GitHub in this GitHub repository. Not just AMD, actually, they have patches for every vendor. And I think they just extracted them from the BIOSes. We started looking at them, and we were assuming that all of these patches would be encrypted, but we quickly noticed that they were, in fact, not encrypted. At least many of them were not encrypted. And, well, that was surprising, but then we started looking at the format, and the format of a microcode update for AMD looks a bit like this. You have some header, which we'll talk about later, and then you have all the match register and mask registers, which we talk about, and then patch bundles. One patch bundle is 4 microinstructions plus sequence word. And basically, this is all we had. Remember, at this point, we didn't yet have the ability to load our own microcode. So all we could do was to statically analyze this. And remember that the microinstructions are completely undocumented. This is some kind of internal implementation detail of the CPU. AMD doesn't document it at all. So this was like, all we could do was something like this, where we could plot the probability that one bit in the sequence word would change together with another bit. And this already, like, you can see some patterns here. This already tells us something. You can kind of reveal the structure of some of the microinstructions, tell you where some fields are, but doesn't really do that much. And one thing that actually gave us a head start was one specific microcode patch, which, to the best of our knowledge, is the only microcode patch where AMD documented what it does. And it's the patch for a CPU bug called red bleed. Now, AMD documented that if you load this patch on your CPU, after you load the patch, there's one bit in one MSR which is now set to 1, even if it was 0 before. So we thought, OK, this is like pretty simple, and it's probably like not a lot of instructions, so let's look into it. And if you look into it, this is what you see. And you're like, OK, well, this is like, looks like a lot. But in reality, if you diff it with the previous patch, it's actually not that much. It's only 4 instructions that got added in this patch, these 4. And one of them is an op, so it doesn't do anything. And we knew it was an op because this bit pattern appears everywhere. So we just thought it's an op, probably. And then the other 3, well, we know what they do. They have to read a value from an MSR, they have to set this bit, and they have to write the value back to that MSR. So first one is probably reading, second one is maybe logical or something, and the third one is writing. And this is like going to be very important later, because this patch tells us how to encode memory reads and writes. This later will be very important. Now, unfortunately, most patches look nowhere near this simple, and this is an example of a different patch for a different CPU bug called Zen bleed. And in this case, like, the patch is much more complex. It uses conditional branches. It uses raises exceptions. It does all sorts of things that at this point we didn't really understand. So yeah, this was like kind of has some limits, but it gave us a head start. So, but now let's go back to that header that I mentioned before, and let's see what's inside. So if you look at this. You see that there are 32 bytes of metadata header, and this is kind of documented in source code and manuals from AMD. And then there are some blocks of data that looks random, and then is the data that we talked about before. Now, if you look at these blocks, we actually know that these are 3 different blocks. Well, first of all, because the first 256-byte blocks is random and changes in every update, whereas the other 2, the green and the orange one on the slides, are random, but they are the same in every update. And also, if you try to change any of the data inside of these random blocks or in the payload, the CPU stops accepting the update. And even more importantly, how long it takes to reject the update changes. If you change the data in the payload or in the first random area, the CPU takes a long time to reject the update. If you change the data in the random sections in between, the CPU rejects the update almost immediately. So we can tell that they're not the same. So one hypothesis that we made is that the first block is a signature, then there's a public key, and then the signed date is at the end. And it will make sense that the CPU rejects the update immediately if you change the public key, because it simply has to check that the public key is correct. And it will take longer to reject it if you change the signature or the signed data, because then it has to verify the signature, which takes longer. So yeah, like we discovered that the first block is a RSA signature, the second one is RSA public key for the signature, the third block is something else related related to RSA, which is kind of irrelevant for this talk, so we will not discuss it further, and then comes the actual signed data. This is an example of a real signature from a real microcode update. We can raise the signature to the power of E, which is hex 10,001, modulo the modulus, which is the green thing. And it gives us this. And this is like some standard way to encode an RSA signature. You have this like one FFF, 0 byte, and then you have the hash of the data that you're signing. And one thing that kind of stood out immediately when we saw this is that the hash is only 16 bytes long. And we thought to ourselves, why is that? Because if you know anything about digital signatures, you know that you should be using a hash that is at least 32 bytes long to prevent things like birthday attacks and whatever. And the only hash functions that have a 16-byte digest are legacy things like MD5 or whatever. So we thought, okay, this looks a bit suspicious, and maybe this is broken, so we should look into it. Unfortunately, at this point, we hit a roadblock, because we couldn't figure out what hash function AMD is using for the signature. It's not MD5, it's not SHA-1 or SHA-2, but truncated, it's not Blake, it's none of these standard constructions that we could think of, and like we couldn't do anything, we couldn't make progress. So we hit a roadblock. And now, SPQ is going to tell you how we reverse engineered this mystery hash and got unstuck.
Right. I will tell you how we traced the microcode update routine with a CPU feature called IBS, or instruction-based sampling. It's a performance monitoring feature from AMD. As Nspace already was telling you, we were measuring the latency of the microcode update routine. And here is an example how this could look with RDTSC. We were also experimenting with this feature called IBS. We found this feature through a blog post that's linked here. Really interesting blog post, shows about some internal information that comes up there. How does IBS work? Or IBS op, to be specific. It's based around a counter of executed microcode instructions. And it also has a configurable maximum. Whenever the counter reaches the configured maximum, then the counter is reset to 0, and information about the previously executed microcode instruction is put into some internal buffer where you can later fetch it from. The information that is put in this buffer is, for example, it consists of the type of memory access. For example, if data was written or read or both, the size of this memory access, the virtual address, if there was any involved, and the physical address. If there is no memory access of this microcode instruction, then we don't get much additional information, and we just say it's an ALU instruction. Now, how would you normally configure this? It's based around an MSR, or model-specific register, called IBS op control, which consists of mainly two subfields. One is the current value, and the other is the configured maximum. Normally, you would configure this in a sampling way. For example, here, you sample one instruction every 1 million executed microcode instructions. But we found that you can also target one specific microcode instruction relative to activating the feature. Here, for example, we would target the microcode instruction number 100 after you start the feature. And if you do this repeatedly, then you get something like a trace. Here, for example, we have on the right side some x86 code that all corresponds to a single microcode instruction on the left side. And you see, we just execute this code 5 times, and then we get this trace on the left side by always targeting the next microcode instruction. And you can also do this for a very complicated microcoded instruction, for example, the microcode update routine itself. And then you get something that looks like this. This is just a very small excerpt from the whole trace. In total, you get like over 1 million microcode instructions in the trace of the microcode update routine. Per instruction, it's not a lot of information, but all of them together tell you exactly how this is implemented. So you just get a little bit information, but you can really understand how they implemented this whole microcode update routine. Now, let's talk about how we use this to identify the mystery hash. This is the microcode update file format again. And if you modify the blue part or the gray part in the bottom, then the update fails. This is expected. But if you modify the green part, the update also fails. And there's the question, why? Because you could change the public key and it could still be valid, but somehow the CPU detects that you modified it. And it turns out that this is typical. Like, instead of storing the whole public key inside of the hardware and consuming, for example, 256 bytes in the ROM, they just store a hash of this. And yeah, they did this here as well. Now, when you run this tracing, this IBS tracing for the Microcode update routine, and you modify the RSA public key, then the update will fail. But if you look into an IBS trace of it, then towards the end, before it basically returns and says it's failed, you see something like this. And this is 16 rounds of some algorithm that is always the same. Every round looks basically the same. The last one is slightly different, but mostly the same still. Let's look into one of these rounds, of the 16 rounds. The first excess that we see here is loading 16 bytes from the RSA public key part of the file update, of the update file. Sequential rounds will always load sequential 16 bytes of this RSA public key. Afterwards, we see 11 constants that are loaded, and all of the rounds load the same 11 constants. The last round additionally loads another constant before doing the normal round stuff. So let's summarize. What do we know about this algorithm now? We know it's based on 16 byte words. It's using 11 constants, except in the last round, an extra constant is used. And there is one algorithm that matches this description perfectly, and it's called ASCMAC. The extra constant that you see, that we saw, it's called K1, and you can see it in the top right of the diagram. The 16 byte words make sense because ASCMAC is based around AES-128, which is 16 byte words. It's always based on 16 byte words. And the 11 constants are just the AES round keys. So this is just exactly what we see. And it turns out this is also the algorithm that AMD used. Now, let Nspace tell you more about ASCMAC.
All right. So if you sketch out the data flow of this hash function, ASCMAC, it will look something like this. You first have to split your data into 16 byte blocks. And then you run each of these blocks through a compression function, which here is called C on the diagram. And the compression function simply XORs the previous state on top of the new block of data, and then encrypts the result with AS, and that's the new state that goes into the next compression function. And the output of the last iteration is simply the hash, and the input of the first one is just 0. And then on the last block, you also have this K1. And the AS key as well as K1 are hard-coded and fixed. They're the same in every AMD CPU. Now, this might look fine. It's standardized by NIST. It's supposed to be a secure MAC. But there's actually a problem with the way that AMD is using it here, which is that CMAC is not a secure hash function. And it's insecure in the way that AMD uses. However, there's a small caveat that you have to know the AS key in order to do something interesting with it. However, luckily for us, this key is inside every single AMD CPU. So we thought that there should be a way to get it. But what do I mean by the fact that this is insecure? Well, the thing is that you can easily construct an inverse of the compression function if you know the AS key. And this is very easy. You just decrypt the state and XOR the alt state on top of the result, and then out comes a block of data. And you can use this to generate collisions, arbitrary collisions in this when it uses a hash function. And the way you do that is that you split your data again to 60 blocks, and suppose that you want this data to match a target hash that you have. Well, you simply run the algorithm forwards on your data, and then from the target hash, you walk the algorithm backwards using this inverse function that you just constructed. And then out comes this other data block, and this is like random. But if you then do CMAC of all of these blocks together, including this new data block at the end, then the hash is always the same as the target hash. And this works for every data, every target hash that you want. So it's very bad when this is used as a hash function. But again, for this to work, we have to know the AS key. And if we go back to the IBS trace, the S key is just there. It's in memory. So the first thing we thought is like, well, let's just read it out. And so we wrote a kernel module to just map the memory, and you get a page fault when you try to access it. The CPU complains that you set a reserved bit in a page table. So AMD must have thought of this and somehow prevented us from doing that. So we thought, aha, we're going to be smart and use non-page mode so that we cannot get the page fault. But actually, you just get, like, you read hexFF instead of, well, getting a page fault. So that doesn't work. We thought about using speculation, but it doesn't work either because write MSR, the instruction that applies the microcode update, is serializing and blocks speculation. So at this point, we thought, OK, the key is there in memory somewhere. And the CPU just cannot read it. So maybe there's some kind of privilege system where the CPU is not privileged enough to read the key. And we thought, OK, there's this thing called the PSP on every AMD CPU, which is supposed to be the most privileged thing on the platform. So maybe we can try to read it from there. And SPQ is going to explain how we did this.
Right. I will tell you how we got full physical memory access using the PSP on one of these AMD CPUs. So what is the PSP? It's a small ARM microcontroller that sits on top of all modern AMD CPUs. It has full access to the system RAM and other resources. It's responsible for booting the CPU and the computer even before the BIOS is active, or the UEFI, or whatever. After boot, it still offers a couple of services to the BIOS and also later to the operating system. In 2018, a company called CTS Labs found a couple of vulnerabilities in Zen 1 CPUs. One of them is particularly interesting. It's called master key, and it's a signature verification bypass in the PSP. How does the PSP boot? It first loads a bootloader from its on-chip ROM, the PSP bootloader, and that's responsible for loading further firmware modules from the BIOS SPI flash that sits on the motherboard. And this SPI flash is organized in a way around the so-called PSP directory. This is a list of all the modules that the PSP might be interested in, together with the location and the identifier of these modules. Then the modules themselves are individually signed. The PSP directory is not signed at all. Now, there are different types of modules. On the left side, we see a code module that is completely signed, as you would expect. And on the right side, you see a configuration data module. Here, only the header is signed. And the header only contains very basic information like the size of the module or if compression is activated. It does not say anything about the type of module or the identifier of this module. And we can use this to create one module in the middle where we take the header from a configuration data module and the body from another code module. And what we have then is a module that looks correctly signed, only the header, but the whole module looks signed, and the PSP accepts it. But we can completely modify the code without any signature verification failing or something. And we use this to add a memcopy service, physical memory memcopy service. Right, so what do we have? We have full physical memory access now, but this only works in Zen 1 and with very old firmware versions. So this is patched and so on, but yeah, we got an old computer and we could do it there, and yeah. So now, how did we extract the ASCMAC key using this? The first thing that you would think is you just read it. You have a memcopy now, but this didn't work. It just returned zeros. Yeah, so we tried that, and it didn't work. So we searched a bit around in this area, and we found something else that was very interesting. We found the so-called CC6 safe area for one of the CPU threads. What is this? This is an area in physical memory, like in your DRAM, where the CPU stores internal data while one of the CPU cores is shut down to conserve power. So the CPU decides that one of the cores is not needed right now, it's just idling, then it powers it off, but before it does that, it stores all the internal data, like current register values and so on, into this CC6 safe area. What we also found that is stored in there is the currently running microcode. You can see stuff like the match registers again here and the instruction bundles later. Sorry. So, how can we use this? We could power down one of the cores, then overwrite the microcode patch inside of the CC6 safe area, and then power up the core again. Now we run our own microcode. Yay! This is what we wanted in the beginning. But also, we can use stuff that we know from before. For example, how load instructions look. We can patch some parts inside of the microcode update routine and overwrite these parts with two loads. One of them loading 4 bytes from the ASCII key, and then a second load that uses these bytes from the key as address, so that it appears in the IBS trace. And yes, this worked. This really leaks the data from the AS key, and you can see in the middle how it looked after we modified the original trace on the left side. This worked for the first D-word, second D-word, and so on. All perfectly. And then, when we loaded everything, we noticed this was just the example key from the ASCII RFC. This would have saved a lot of time if we would have known that before. Yeah, and the same key is used from Zen 1 to Zen 4. So yeah, we exploited it on a very old Zen 1, and we could still use it on a Zen 4. On Zen 5, they changed the key, not the algorithm though. I don't know why, but they changed the key. We could also read this using a different method with direct physical access to the DRAM. But yeah, we don't go into detail here about this. Now, Nspace will tell you more about reading and writing microcode.
All right. So you have the CMA key. Now you can run the attack that I described before. So you simply have to find an RSA key that has the same hash as AMD's key under CMAC, and you make sure that this is easy to factor, so you can factor it. This can even have 3 or more factors. The mathematics just works the same. And then you sign your update using this key, and then you give it to the CPU, and the CPU is going to like, yeah, this looks good, and apply the update. And profit. So we have made a tool that automates all of these steps for you. It's called Zen Tool. It's available on our GitHub. If you scan the QR code there, you can get it. Just search for Zen Tool on the internet, and you will find it. So this is how you write. The thing is, OK, now we also want to read other microcode patches, but there's something that is blocking us, which is patch encryption. And here is a diagram that shows how many of the patches for each generation were encrypted. So you can see that in Zen and Zen Plus, almost no patches were encrypted. Zen 2, some patches were encrypted. And Zen 3, most were encrypted. Zen 4 and Zen 5, pretty much everything is encrypted, which is a problem for us because now we actually want to reverse engineer all of these patches. And we cannot do that because most of them are encrypted. So the first thing that we did once we finally managed to get the CMA key was to try and also break the encryption. Now, let's go back to the IBS trace once again, and this is what the decryption of a patch looks like. You can see that this doesn't look like AES anymore because it's now using 4-byte loads and stores instead of 16 bytes, so it's some other encryption algorithm, but maybe this is some other well-known cipher, and we can somehow identify it. So one thing that we did was to try and dump all of the registers' values during the decryption routine. We did it the same way as before. We took an instruction that is the beginning of the decryption. We replaced it with a load that loads from the address contained in a register so that the value of the register shows up in the IBS trace. And if you do that, eventually you run across this value, which is interesting because if you search for it on the internet, you find all sorts of results. So there's some results that don't look very interesting, which are about some magic hash constant. But there are others that look very interesting, like one about something called the tiny encryption algorithm. And if you open the page on Wikipedia, you find out that the tiny encryption algorithm is an algorithm, or rather a family of encryption algorithms that are designed to have a small code size. And it would make sense that AMD would use something like this because they are constrained by the size of the code in the microcode ROM. Space in the microcode ROM is precious, so it makes sense that it would try to use something that has a very small code size. And specifically, if you take one of the variants called x86, you'll see that this is like actually a pretty good fit for what you see in the trace. So first of all, it's using our constant there. And then if you run through the IBS trace side by side with this code, you look that this looks pretty much perfect. It's really the same code. So we thought, OK, we should, now we think we have guessed the algorithm. Let's try to get the key. The x86 key is simply 4 uint32s. So we, again, dumped all the registers and tried all combinations until we found something that correctly decrypted an update. And that was it. So it's the same thing. And so to our surprise, this also successfully decrypted the updates for Zen 5. Now remember that AMD had changed the RSA signing key as well as the CMAC key on Zen 5, but for some reason didn't change the encryption key. We don't know why, but thank you, AMD, I guess, because now we can decrypt everything. Yeah, so this is how you can do it. And let's also briefly look at how they fixed it. Well, if you go to the advisory page, they tell you that the fix is to install a microcode update. Now, you may think, OK, so if somebody has already loaded a backdoor microcode update, and the code that loads the microcode update is itself a microcode, then this seems a bit like kind of a chicken and egg problem. So the way that we think that this works is that the PSP somehow loads the fix at boot, like before the CPU boots, so that even if you had a bootkit that could load a malicious microcode update, it wouldn't work because the PSP has patched the CPU even before the BIOS executes. And the way that they fixed it specifically is by turning CMAC into this thing called the Merkle-Damgard construction, which is a well-known way of building secure cryptographic hash functions. If you look at the data flow, it looks really, really close to CMAC, and it is very close. And the only major difference is that they turned the compression function from CMAC, which we showed before, into this other thing called Matthias Meyer-Oseas, which is a well-known way to construct secure, which means to say you can not invertible compression functions from a block cipher such as ES. Now, this is all fine. It's like a well-known way to build a hash function from a block cipher. So as far as we can tell, this is fine. Because this is so similar to CMAC, the size of the patch is very small. And in fact, the patch is only like 5 instruction bundles, which is like very, very small. So now what? Well, there are some things that we would really like to do. For example, fully reverse engineer the microcode ISA, which is well, completely undocumented. And if you want to do anything, of course, you have to reverse engineer this. We would like to reconstruct the mapping from x86 instruction to microcode ROM addresses, because you need this in order to patch certain instructions. We would like to document all of these internal registers that you gain access to with microcode. And we would like to find bugs in the ROM, perhaps. Imagine like a bug in the microcode that does VM exit, that lets you escape a VM. That would be pretty cool, no? So for all of these things, we need a dump of the microcode ROM. And thankfully, some friends of ours, which worked on analyzing the microcode from some older AMD CPUs, have gotten some Zen and Zen Plus CPUs and have delayered them and have looked at the ROM under an electron microscope. So this is what it looks like. This is the microcode ROM from, I think, Zen or Zen Plus CPU. This is the microcode ROM, and if you zoom in into the part highlighted in green, then this is what it looks like. You can really see all the bits one by one, so you're looking at bits now. And if you then take a picture of every part of the ROM and then stitch them together and figure out how the bits are encoded in the silicon, you can then get the dump to the ROM. So this is like going to take some time, but we think this should be possible. It's also been done before from older ones, so we know it also works. And they also wrote a new disassembler, an assembler called ZenUtils, which has some other features that ZenTool doesn't have. For example, it lets you do branches to labels. And they even implemented strlen in microcode. Strlen, the C-library function. So this is like what they wrote. You can pass a C string into RBX, and this instruction will compute the length. And you can find this on their GitHub. And this is the QR code is a link. Now, there's going to be a live demo this time. So let's see. We have a demo.sh, OK? So we are trying to backdoor RDRAND to make it return 4 all the time. RDRAND is an instruction that is supposed to return a random number every time you execute it. So first of all, we ran a test to make sure that this is still working properly and it's returning random numbers. And as you can see, this is returning random numbers. This is fine. Now, we're going to backdoor the patch that is currently applied on the CPU. So we downloaded it from the GitHub repo that we talked about at the beginning. It's there, and we replace, we are using some bundles that are unused in the patch, as well as a match register that is also unused. And we replace them with some instruction that XORs reg4 or register, and then makes the value 4, and then finally returns to the next instruction. So we do that, and then we try to apply our new update, and it fails. Well, it fails because we changed the data, but we didn't update the signature. So of course, now the signature is invalid, and so the CPU rejects this new update. Zentool is helpful and tells you that you might have not resigned the update, so you should do that. And if we run Zentool verify, it will tell you, yes, the signature is bad. So we simply have to run Zentool resign now. So this will resign it, and if you try to load it again, this time the CPU takes it. This is on this machine that is here, so the one I'm doing the presentation now. And now if you run rdrand, again, this time it returns 4. And if you run it again and again and again, it will also return 4. Now, if you want to talk to us about this, you can find us on the camp phone network, or if you want to talk to us after the camp, you can find us on Mastodon, on the Fediverse. And feel free to ping us. Feel free to, if you want to play with this, we have this machine that is vulnerable, and you can play with it. If you have your own AMD machine, then also works. And finally, oops, go back to the slides. Live demo, yes. Is this working? Yeah. Thank you. Thank you, everyone. Thank you for coming here. Thank you for coming here, and also thanks to the content team for having rescheduled us after the power outage on Friday. We were supposed to be on Friday, and they found us a spot.
So, do we have questions? Are there questions in the room? If there are questions, can you go to the microphone?
Hello. First of all, really, really cool talk. Very much enjoyed it. So basically, after you did the live demo now, this means that this laptop will always generate 4 as a random number unless you actually install a new microcode update, right?
Yes.
Our demo installs the original patch again to make sure the system stays stable. Sudo was not working for whatever reason. So.
Nice.
Interesting. Okay. So basically, you probably shouldn't use that machine right now to generate new SSH keys or something like that, right?
Probably not a good idea, yeah.
So the thing with rdrand is that when this came out, people were very, very afraid that the NSA was was backdooring it, and it was unsafe to use. So Linux actually doesn't trust rdrand in the default configuration, and it will also use other entropy sources. So the good news is that you too can backdoor rdrand, not so you can do it yourself. But yeah, so I think in theory it should be fine, but yeah, don't do this on a production system maybe.
Any other questions?
I have a small comment. There's also a CTF here at the camp, and there's also a challenge using this research. So maybe have a look at this.
Please.
Yeah, hi. Thanks for your excellent talk. I wondered, at some point you said you read the AES key directly from DRAM.
Yes.
Why was the key in DRAM?
This area where the CC6 safe state is stored, we think AMD also uses the same area for some temporary data. For example, this key. And this is why, I think. I don't think this was working from Zen 1 to Zen 4, but in Zen 5 it became possible. Probably they made some code changes. I don't know.
But it must be in ROM as well, right?
It's also in the ROM, yes. But we don't have a ROM dump of Zen 5, so we couldn't use that. Or for Zen 4 either.
Thank you. Next question.
Right. You mentioned that it persists with the random number that it persists if you do this, so across reboots as well?
No, so the way that it works is that when you reboot the system, the currently installed microcode update is removed, and the BIOS just reapplies it every time the machine boots, right, or the PSP or something.
So the chip contains its own microcode, and then the microcode RAM is reloaded every boot. Okay.
Correct, yes.
The path to persistence should be fairly self-explanatory, I think.
Did you check if other low-power AMD CPUs were also affected?
To the best of our knowledge, every AMD CPU is affected, starting from Zen all the way to Zen 5.
Okay, and do they also use the same instruction set if you checked, like among all the generations? Because like, the internalizer.
So we know that the microcode ISA changes a little bit between generations, but it's mostly the same.
The number of instruction bundles also changes per generation. Like they added more space in the RAM.
There is a design principle called parsimonious design, where you basically reuse as much as possible across like generations and only change what you really need to change, which means that errors like this persist.
Yes.
It's kind of beautiful.
Oh, this is actually part of my previous question. If it's in ROM, the microcode must be able to read the ROM. It must do that to copy it to the RAM. Why not read from the ROM directly, do you think?
So no, the only thing that is in RAM is the microcode update, the microcode patch. So the microcode ROM and the microcode RAM coexist. So the CPU can directly fetch instructions from the microcode ROM. And we think that there should be a way to read the microcode ROM from microcode, but we haven't found it yet.
Yeah, I meant the AES key.
So
the AES key.
What I think happens is that they have it in ROM, they load it into a register, and then because they want to use it later, they store it in a temporary area, which is in this DRAM area, to just be able to access it later again. Sure, could be made differently, but they decided to do it this way.
To their loss.
Next question.
Yes. Have you also found any ability to create new macro instructions?
We know that we can modify in the microcode engine the part that does controls fast path instructions, and maybe this would also allow this. But the instruction space is quite dense, and everything is basically used. I don't know. I don't know exactly. We have not fully tried it, but could be possible.
A topic for future research.
Yes.
If I may ask another question. So, did you find any spare instructions that were perhaps used as testing?
Sorry, I didn't get the question.
Did you find any spare opcodes that could be enabled for debug use?
Maybe. We did not look into exact details.
I don't think we have found anything. Maybe they exist. I think if we had a dump of the ROM and a way to know which address each instruction maps to, we might be able to find them if they exist, but we don't know of anything like that yet.
Okay.
I believe that you have your next next camp talk already laid out right there. I expect to see you here next time for that follow-up talk, right?
That would make that the second vendor I would have that talk on.
Do we have any questions from the internet? No? All right. I know, I was half expecting it's like, like something like this, like I would expect nerdy questions from the internet. Do we have any other questions? Going once, going twice, going 3 times? Thank you very much, Nspace and SEX.